Hello, this is Brooke Hollingshead. This is my second video presentation for Math 510. This one is on the column correspondence property, or the CCP. First, I'm going to kind of a rough proof of it. So the CCP states that any column in matrix A can be written as a linear combination of the other columns if the same thing can happen for the columns that are in the row reduced echelon form of matrix A, which we're going to call R. So we're going to start this proof by assuming that that is true for the columns and show that that makes its way down to the same thing but for the reduced row echelon form. So I'm going to multiply an elementary matrix E times each side of this equation to start by the sum of the linear combination of the other columns. And this is the same thing basically as the sum of E times each of those columns, or E times the linear combination of those columns. And actually what this means is if I multiply E times a matrix, that means I'm multiplying E times each column of the matrix, column I all the way through column N. And actually I could just multiply E times each of those columns individually. E times column N. And this is really the reduced row echelon form of that matrix. When I take the elementary matrix times each of the columns, and I go through and I end up with my reduced row echelon form. So I get matrix R. So what this tells me is that each column, when I multiply it by E, I should get that same column in the reduced row echelon form. And because of this, I can look back up here at this and say, okay, I'm going to take this and say E times column A of J really is just column J of R, my reduced row echelon form. And over on the other side, I can take these pieces and do the same thing and say, all right, that's the sum of the linear combination, or it's the linear combination of that column in the reduced row echelon form too, which gets me back up to where I was going in my proof. So if this one, then the other one. So that's basic, fast proof of the CCP. Using that now, we're going to say, all right, so let's say I have this set of vectors. I'm going to take this and go through and do some real quick row reductions. I'm going to take row 2 minus R1, take row 3 minus 3R1, row 4 minus 4R1, and I can do all of those at the same time because R1 isn't changing. So I have 1, 0, 1, 1, 2, 3 minus 2, 1 minus 2, 2 minus 3, 4 minus 3, 6 minus 4, 2 minus 4. Okay, and from here, I change the sign on row 3. I take row 4 minus 2 of row 2's. I can pretty much get rid of row 4. Over a little bit. Changing the sign, getting rid of this one. And now if I add row 3 to row 2, I get rid of that one also. So, reduced row echelon form shows me that my pivot columns are just column 1 and column 2. Column 3 and column 4, by inspection, if you look, I can use those two to make, I can use my pivot columns 1 and 2 to make 3 and 4. I can add column 1 and column 2 together to make column 3. I can subtract column 2 from column 1 to make column 4. So that means that my first two columns are my pivot columns. What CCP tells me is if I can do that with those columns, then I can also do those with the original vectors. And with the original vectors, that tells me that if these are my pivot columns, I really only need those two to make the other ones. Then the same goes for my vectors. So my basis for this span, I really only need those first two. I only need 1, 2, 3, and 4. And you can check the math on that too and see that if I add these two together, I get the third one. And if I take the first one minus the second one, I get the fourth one also. So I only needed those first two vectors. Those are my basis now for the span of S. Okay, so what's nice about using the CCP on that then is to check and see if other vectors are in the span. So I'm going to check right now and see if this vector 2, 5, 5, 10 is in the span. I only have to use those first two vectors. I don't have to use all of them because just those first two are the basis. So I can say, all right, if I take 1, 2, 3, and 4, and I take my second one, so those are my basis, I can check other vectors just using those two and see if this one works as a linear combination of those. So I'm going to do pretty much the same row reduction operations that I did on the last one. Row 4 minus 4R1. And we should get 1, 0, 2, 0, 1, 1, 0, negative 1, 5 minus 6, 0, 2, 10 minus 8. Okay, so I'm going to get rid of, I'm going to take row 3, and I'm going to get rid of also row 4. So we end up with 1, 0, 2, 0, 1, 1, zeros, and zeros. So column 1, column 2, column 3. I can see that column 1, if I take 2 of these and add them to column 2, I get column 3. Column 1, 2 of them, plus column 2 equals column 3. CCP tells me, okay, that's the same thing then for my vectors. If I take 2 of the first vector and add it to 1 of the second vector, then I get the third vector, or their entries at least. And so I can see, because this third vector can be written as a linear combination of the first two, then yes, it is in that span. And CCP helped me not have to do as much math because I only had to use those first two columns, or first two vectors,